Welcome back to this episode where we will talk about linear regression with LASSO. Before we start, just as a disclaimer, we will not go into all of its details, but after this episode you will know why we apply LASSO in machine learning and when it could be a good choice of using it. LASSO stands for Least Absolute Shrinkage and Selection Operator. This acronym sounds cryptic when you read it for the first time, but after this episode you will understand why this acronym describes it pretty well. So why should you bother about LASSO? Well, LASSO belongs to the general family of regularization. We distinguish between two regularizations, explicit and implicit. And we will see that LASSO belongs to the explicit regularization group. Regularization is used in machine learning in order to prevent our model from overfitting on the training dataset during training. So what is overfitting again? Well, overfitting happens if our model follows the characteristics of the training data too close. But remember, our goal in machine learning is not to find the best model on the training data, but on the test data, or ultimately on the real data that is hopefully represented good enough by our train, validation and test data. So how does LASSO works? And for that, let's switch to our board. So let's talk about the math and the idea behind it. Before, our loss function, aka objective function, was only having one component, the mean squared error loss. You probably know the definition by heart now. LASSO extends our objective function by another term, which is equal to lambda times the sum going from I equal to 1 to f, where f is the number of features over the absolute value of wi. Note that this lambda times the L1 norm of the weight vector. Also, it is always good to remember how the LP norm looks like. I wrote it down on the right hand side. Plug into it p equal to 1 and you get the L1 norm. Now, our objective function is extended by this LASSO term, which penalizes our model whenever the weights become larger. The larger the sum of absolute values of our weights, the higher will be the contribution from the LASSO term to our overall objective function. Thus, during the training of our model, we will not only minimize the mean squared error, but also find the lowest set of values for the weights in order to minimize the LASSO term. As you could guess, the LASSO term is working against our mean squared error, and that is why it is called a regularization function. Imagine it is as playing football but with two referees instead of one that need to decide together whether a play was a foul or not. Also, lambda is a new hyperparameter that we introduce, and you as a machine learning model trainer have to decide which value to choose. This may be tricky because the higher you choose lambda, the more the LASSO contribution will dominate the overall objective function. If you set lambda to 0, you will simply get the mean squared error. Lambda has to be greater than 0 and can go up to infinity. In future episodes, we'll find a way on how to choose a good set of hyperparameters in a more systematic way. Of course, we also need to recompute the gradients. So what is the gradient of our new objective function? Well, our objective function is the sum of two components, the MSE plus the LASSO term. We already know the gradient of a mean squared error, so we only need to compute the derivative of a LASSO term with respect to our weights. Again, the LASSO term is equal to lambda times the sum over absolute values of our weight components, so we need to know what the derivative of the absolute value of x is in order to evaluate this derivative. So let's start simple. Let's have a look at this graph, showing a plot of the absolute value of x against x. As you can already see, the absolute value of x is everywhere differentiable except at x equal to 0. That is a problem, but we can solve it with a little bit of mathematical trickery. Don't show this your math friends, they will react allergic to such math tricks. So we see that the slope for the part with negative x values is equal to -1, and the slope for the part with positive x values is equal to 1. The problem is at x equal to 0, where we can draw several tangent lines. So what is this trick in order to define derivative? Well, mathematically spoken, there is no function derivative because this function is not differentiable at x equal to 0. But Let's have a look at subderivatives for a second. Here we got a proper definition of a subderivative, but forget it for a second. Essentially, subderivatives generalize the derivative to convex functions, which are not necessarily differentiable. In our case, the absolute value of x is indeed convex, because you can take any 2 points on the function and draw a line between them, and these lines will always be at least on the level of the function curve. So for this function, the subderivative is given by the set -1 for x smaller than 0, the interval -1 to 1 for x0 equal to 0, and the set +1 for x0 greater than 0. So as we could see previously, we could draw any tangent line and at x equal to 0, which slope was going from -1 to 1, and this is exactly what we get here for the subderivative. These sets that contain only one element are known as singletons, and whenever the subderivative contains a singleton, we know that our function is differentiable at those points. So as a quick consistency check, the only singletons we have are -1 and +1, and that is what we already know from before. Now comes the trickery. We simply pick a value out of this interval and assign it to a derivative of our function at x equal to 0. Here we simply pick the point that is in the mid of the interval boundaries. So 0 because 0 is equally distant away from -1 and +1. So our derivative for the absolute value of x is now defined as +1 for x being greater than 0, 0 if x is equal to 0, and -1 for x being smaller than 0, which is equal to the sine function of x. Again, in a strict mathematical sense, the derivative is equal to x over the absolute value of x for x being not equal to 0. Another trick for functions that are classically not differentiable, we could use a method which is called distributional derivatives. But this would be overkill here, so let's move on. So with our new knowledge, we can finally write out the derivative of the LASSO term as being equal to lambda times a vector that contains the sine function of the weight components. And we also transpose it. You're asking why? Well, I have made an entire video about this. Check this info card above if you wanna know more about it. So in total, our gradient of the objective function looks like this. It is equal to the MSE part plus our gradient of the LASSO term. If we check the dimensions, we can see that it matches and is consistent with each other. Enough math. Let's talk through some plots I have made, and then afterwards I show you the code on how to compute the gradients. So let's switch back to the presentation. So I have generated a new linear dataset with 2 features, and this is what we get. For this video, I didn't split it into a train, validation and test dataset, but just took the whole dataset for the training, since we are interested in how LASSO is working. The training was conducted as usual with stochastic gradient descent with mini batches. Also, I have conducted the training once with only the mean squared error in our objective function, and once with the mean squared error plus the LASSO term. After training the linear model with 100 epochs, a learning rate of 10 to the power of -4 and lambda being equal to 0, we get the following model fits. As you can see, the model is the same for the mean squared error and for the mean squared error plus LASSO, as expected, since lambda is equal to 0, right? This is another view on the data with the fits. This is the loss history of the average loss against the number of epochs, and as you can see here, the curves are lying on top of each other. Mean squared error and mean squared error plus LASSO are absolutely equal. When we set lambda equal to 20, we will get the following result. As you can observe, we see a difference now. The green curve is model trained with the mean squared error plus LASSO, and the red curve is the model trained only with the mean squared error. The loss history also shows the difference. The average loss of the mean squared error plus LASSO is larger than the average loss of the mean squared error, since our regularizer is taking effect. This is typical when you use regularizers, but this doesn't mean it is bad or good. It can be good when the performance on the test set becomes better. So to speak, our model generalizes better. In this case, our model is indeed performing worse, but that doesn't matter for now. This is just a toy dataset. I want just to show you the effect of LASSO. Now let's move on to our fit for lambda when lambda is being equal to 100. Now we can see a large difference between both models. As you can see, although we have the same model in both cases with the same starting weights, we get a different result because of our object function that is steering the direction of the weight development. What you can observe here is that for the model that was being trained with mean squared error plus lasso, it has a slope along the x1 feature that is quite large, while the slope along the x2 feature is very low. It is almost constant. When you have a look at the red area, you can see that the slope along the x2 axis is much larger. Again, a fast look at the loss history reveals, as we would expect, that the average loss got even worse for our LASSO plus MSE model. So as you can see, you have to be careful when you choose the lambda value, because it can help your model not to overfit and generalize better, but it can also harm your model when the LASSO loss becomes too large and hinders the objective function to get to the optimum. Here is a table that summarizes our findings. So the columns are representing the weights that belong to the x1 feature, the x2 feature and the bias term. The rows represent the training method, so we started off with the following set of weights: minus 1.255, minus 0.107, minus 0.243. And after training with mean squared error and lambda being equal to 0, we get this 2.761, 0.753, 0.233. We get the same result for mean squared error plus lasso, where lambda is equal to 0, as expected. When we set lambda equal to 20, we see that the weights associated to x2 and the bias term are becoming suppressed and become smaller. The weight of the bias is almost 0. When we increase lambda to 100, we can see that the weights of x2 and the bias term are now very close to 0, and the weight of x1 is also substantially lower. So as we have thought, the lasso term lowers the values of our weights and tries to zero them out. The less important feature weights are getting faster to 0. And the more important feature weights are also becoming smaller, but at a much smaller rate. So LASSO can help us to find out which feature weights are more important than others, but if we overdo it, we lower our important feature weights too much. Let's have a look at the actual weights that are associated to x1 and x2. Those are 3 and 0.1. As we can see, the MSE was driving weight associated to x1 to 3, but the feature weight of x2 was a little bit too large, probably picking up the noise that I introduced into the data. With LASSO we could lower the weight value of x2, but we were still far away from 0.1. The main takeaway from this episode should be that LASSO was originally applied to linear regression models, but can be also used for non-linear regression models. LASSO is a regularizer that is added additively to the objective function. LASSO is used in order to zero out lower sum weights, especially those weights which are less important. So now I want to show you how we can compute the LASSO term and how we compute the derivative. So I will essentially show you the code on how I did it. And yeah, this should give you an idea how to implement it. The rest you already know. So let's dive into the code. So this is the code for today's episode. Most of the code you already know when you followed the previous episode. So we have again our custom dataset. We have again our simple model, linear regression model. We have our mean squared error defined here, the gradient of the mean squared error. Here come the new things, which we'll talk about in a sec. And in our main function, I just prepared some code in order to generate the plots that you've seen previously. You should know how to do it by yourself by now. Basically what you would do is you generate your toy data, right? You prepare your design matrix X. Then you generate your weights, which are randomly assigned values. And then you just go on, right? You create the dataset, the data loader I created with the batch size of 128 without a shuffle. Here you can see the learning rates, the epochs, different kind of numbers I tried out. And this is just plain stochastic gradient descent. You should know by now how you do it with mini batches, right? So let's come to the interesting part. So the interesting part is playing here. This is the LASSO term which I talked about. So what we need for the LASSO term is simply a lambda value, right? And the weights. And what we then compute is just simply lambda times, and then we can use the numpy linalc norm function in order to compute the L1 norm for our weights. Simple as that. But it would be also not a problem to do it yourself, right? You would just do a for loop over all the weight values. You would just sum them up, take the absolute value before for each value, right? And that's it. And the mean squared error lasso, this is our new objective function, right? Where we have the mean squared error plus our lasso term. That's it. And then we of course needed also the gradient, right? And what I did essentially was, okay, we need the sine function on all the components of the weights, right? Since we are dealing with NumPy, we can simply plug in the whole array into this function and get the sine function applied on each component. And then we simply have to add. We simply do MSE gradients plus lambda times a sine function, right? This is what we calculated the gradient of the lasso term. And that's it. And then you just train as usual, as you know. And voila, you have lasso integrated into your objective function. I would suggest you to code it up yourself and play around with different numbers of lambda and see how the loss history is changing and also how the model fits look like. So I hope you enjoyed this episode and you have learned something new, that it was insightful. If yes, then please subscribe and like, and I see you in the next episode.